Hi, today I'll present the results from a literature survey we did on systems that automatically extract temporal information from text, focusing on those systems that use some form of temporal reasoning. So with temporal reasoning, we mean combining small pieces of temporal information to obtain a more complete temporal picture of the text. So for a bit more background about types of temporal information that can occur in language and the frameworks that are generally used for temporal reasoning, I refer to the 5-minute talk I have about this topic. And in this talk, I'll focus on the results of the survey and discuss the found approaches to integrate temporal reasoning into machine learning-based temporal information extraction systems. I'll start with a small example of how many temporal information extraction systems work, following the pipeline used in the Temporal series. So imagine we encounter the following sentence in a clinical report. So after she had an episode of aphasia, she underwent a head CT and a neuroconsult on the 2nd of November. So we often know the document creation time, for example, from the file itself. And then the first step is to find the event mentions of interest. So in this case, there are 3: the episode of aphasia, the CT scan, and the neuroconsultation. A second step is to find the temporal expressions in the text, which could be explicit mentions of dates, timings, or durations. So in this case, you have 1, the reference to the 2nd of November. Another step, where temporal reasoning is sometimes already used, is the normalization of such expressions. That means interpreting that the numbers 11 and 2 here actually refer to the 2nd of November, and in this case, in 2001, as the document was written in this year. And the third step is to extract the temporal relations between all entities, so finding the temporal relations among the colored boxes in the image. So performing this last step accurately is still a big challenge in temporal information extraction, and is also where temporal reasoning plays a prominent role. So in the survey article, we focused on systems that perform this task, using some form of symbolic reasoning in doing so, and have been published in the last 3 decades. In the remainder of the presentation, I'll restrict to temporal relation extraction systems, as these were found to most prominently use temporal reasoning. For reasoning and other extraction tasks, I'd like to refer to the full article. We found that reasoning has been used in all phases of system development, from annotation to evaluation. I'll discuss the results for each of these phases, starting with annotation. So manual annotation of temporal information has shown to be a quite difficult and time-consuming task, during which annotators frequently miss relations. So the way temporal reasoning has been used here is to reduce the number of entity pairs that annotators have to label, by performing reasoning after each annotation step, preventing annotators from having to label pairs that can already be inferred from currently annotated relations. To illustrate this, I have a small animation how this would help in this example. If one was asked to annotate all currently present relations, starting with the blue one. We can see that after annotating 2 relations, a third relation can be inferred via the transitivity of before, and it thus no longer requires manual annotation. And we can continue doing this and save another label here, and so on. So using temporal reasoning here can help to reduce the annotation load, and at the same time improve the consistency of the resulting graphs. Then, once a dataset of text has been annotated with temporal graphs, some works have used temporal reasoning to increase the number of relations in their training data. I'll be quite brief about this. So in some cases, augmenting the data with additional relations has resulted in better extraction performance, but not consistently. So in some cases, it even decreased performance. Its effectiveness seems to depend on whether reasoning is also used in the next phase, during training and prediction. So before I dive into the methods here, I'd like to give a quick motivating example on how reasoning could help prediction, which is often a sub-procedure of model training. Imagine we have our sentence from earlier, but we now ask our system to make predictions for these relations. And let's say we have a good system which correctly predicts this graph. Beautiful. But let's say this report was written at the end of the day, so the sentence might have contained a tiny mistake. So unfortunately, this is a bit confusing to our extraction system, which reads a present tense now, instead of a past tense. and may now predict that the episode of aphasia occurred around the time of the document was written, instead of in the past, resulting in an overlap relation. So this is where temporal reasoning may save the day, because it can detect this temporal inconsistency and use the evidence from other parts of the graph to help infer the correct relation. So similar principles have been integrated in many ways, because as you can imagine, when this graph becomes big and more types of relations are used, this reasoning step may become more and more computationally complex. Some frequently used methods are listed here. In greedy inference, relations are added one by one to the final graph in order of confidence of the predictions. Post hoc conflict resolution methods first construct the entire graph, then detect the inconsistencies, and then try to resolve them by deleting relations. Then there are a number of works that extract groups of relations in phases, called sieves. They apply a sieve to extract a number of relations and then perform a reasoning step over the graph to further complete it. This process is repeated for each sieve. The sieves are usually applied in order of precision, starting with high precision sieves, and this way the number of times reasoning has to be performed is smaller and more local, reducing some of the complexity. So there are a number of approaches that aim at more globally consistent graphs, including Markov logic networks and integer linear programming approaches, which see prediction as a constraint optimization problem of finding a consistent graph that receives the highest score from the extraction model. So in some cases, the extraction task is formulated as a structured learning problem, where the extraction systems are optimized already at the training time for extraction quality via the reasoning-based prediction procedure. So instead of training extraction system independently from the reasoning procedure. A trend that we observe is that most studies compared the use of reasoning during prediction versus not using reasoning at all, from which we observe that the trend that using some form of reasoning generally improves extraction performance. And although no empirical comparison of all methods was made, several articles make pairwise comparisons between reasoning methods. And in these, we observed that carefully extending the integration by using global reasoning methods and also integrating reasoning at training time overall increases overall extraction performance. Finally, a different approach that we proposed ourselves is direct timeline modeling, which tries to circumvent the relation extraction problem altogether and directly predict start and end points for the events, from which by definition it is not possible to end up with temporally inconsistent predictions. An important note to make is that the expressiveness of the used temporal reasoning frameworks seems to increase over time, starting from reasoning with a few basic Allen interval relations to more extensive reasoning with partial information based on point algebra. Finally, I'll very briefly mention evaluation. So not because evaluation is not important, but as there is quite a strong consensus on evaluation of temporal graphs, at least for TimeML style data. And since its use in the Temporal 3 shared task in 2013, most systems are evaluating using an F-measure based metric called temporal awareness. This metric reflects a similarity between a predicted and a ground truth graph after the reasoning has been performed. So to conclude this presentation, it has become more clear that temporal reasoning is more and more being exploited in temporal information extraction systems, but often the current system address the extraction of just a part of the temporal information in the text and missing some of the opportunities temporal reasoning may bring in combining these pieces of information together. So some areas that received less attention are representation of uncertain temporal information and how to combine symbolic and quantitative reasoning. So with this remark, I'd like to end, and thank you for listening. Of course, if you have any questions, remarks, or would just like to discuss this topic sometime, feel free to send me an email.